Welcome to the Deep Dive. Today, we're taking a look at computer science. We're using Wikipedia mainly, trying to sort of unpack what it's really all about.
Right, not getting lost in the weeds, but really getting the core concepts.
Exactly. And hopefully showing you, the listener, what it means beyond just, coding.
Yeah, because it's incredibly broad, isn't it?
Yeah.
You've got the real deep theory stuff, algorithms, computation theory,
hmm
all the way to like building hardware, software design, AI, security. It covers a lot.
And there's the central question we'll keep coming back to, which I find fascinating. What can actually be automated and what can't?
That's the key. And it's older than you might think. It's not just about modern machines.
Like the abacus or ancient algorithms, those early steps, right?
Absolutely. Early forms of algorithmic thinking. So maybe let's try and define it first. Computer science.
Good idea. What is it? The definitions vary a bit, don't they?
They do. You see, the study of computation, information, and automation, or the systematic study of algorithmic processes.
And there's that whole debate about whether it's like a science in the empirical sense.
Right. Testing programs and such.
Or more like mathematics, because code has that logical structure.
Or even engineering, focusing on design, reliability, making things work dependably.
It really feels like a blend of all three sometimes.
hmm And people have suggested other names too, like computing science or informatics. Data science is huge now, of course.
Informatics really highlights the information aspect. I like that quote. Computer science is no more about computers than astronomy is about telescopes.
That's a classic. It gets to the heart of it. The machine is just the tool, right? The real subject is, well, computation itself.
Okay, so let's jump back in time a bit. The history here is actually pretty cool.
It really is. You've got Leibniz
Yeah.
way back thinking about the binary system. That's fundamental. 17th century.
Incredible. And then Charles Babbage in the 1800s,
Yeah.
the difference engine, and dreaming up the analytical engine.
Which was basically the concept of a programmable computer, inspired by Jacquard looms and their punch cards. A huge conceptual leap.
And Ada Lovelace, she saw the potential, didn't she? Wrote what many call the first algorithm meant for a machine.
Yeah, specifically for Babbage's analytical engine, calculating Bernoulli numbers. Amazing foresight.
Then you fast forward a bit. Hollerith uses punched cards for the U.S. Census, that tabulator machine.
Which eventually led to IBM, right? So there's a direct line there.
It's wild that Babbage's programmable dream was sort of realized much later with things like Howard Aiken's Harvard Mark I with IBM's backing.
And that's around when the word computer shifted,
Right.
from a person doing calculations
Ah, right, like human calculators.
to the machine itself. That was the 1940s. And then you start seeing the first actual computer science departments popping up. Cambridge, Purdue.
Columbia, too, wasn't it? With IBM involved,
Yeah.
that's when it really became a formal academic field.
Okay, so what are the foundational pillars? What's at the core?
Well, the Computing Sciences Accreditation Board, CSAB, they list a few key areas. Theory of computation is a big one.
Yeah. What's computable, what's not, how complex problems are.
Right. Then algorithms and data structures, the basic building blocks for solving problems efficiently.
Can't do much without those.
Mm.
And then programming languages and methodology, how you actually tell the computer what to do.
And finally, computer elements and architecture, the hardware side of things.
And within that theory part, you have huge honors like the Turing Award,
The Nobel Prize of Computing, basically.
pretty much. And these massive open questions like 2 any versus n.
Ah, yeah, the million-dollar question. Basically, if you can easily check an answer, can you also easily find the answer? Still unsolved.
Still unsolved. And then there are those 3 great insights that Bill Rappaport talked about. Really simplifies things.
Oh, yeah, those are neat. First, anything can basically be represented with just B's and 1s.
The binary foundation.
Right.
Second, a computer only needs like 5 basic actions.
Yeah.
Really fundamental operations.
And third, you only need 3 ways to combine them. Sequence, selection, like if, and repetition loops. That came from Bo and Jacopini.
It's kind of mind-blowing how much you can build from such simple ideas.
Totally. So how does this connect to, the things you actually use? Applied areas.
Well, all that theory powers everything. The computer graphics, making images and animations,
Okay.
artificial intelligence, trying to get computers to solve problems, learn, understand language, see, a huge field.
Right. AI is everywhere now.
Software engineering is about building those complex apps reliably. Then there's computer architecture, designing the chips, networks, connecting everything.
Security, cryptography to keep data safe. databases to manage all the information.
Exactly. It all stems from those core principles. It underpins so much of modern life.
So wrapping this up then, computer science is, well, it's huge. It's constantly evolving,
Hmm.
grounded in some pretty deep theory, but touching almost everything practical.
Hmm.
And it always comes back to that question for you, the listener.
What can be automated?
Exactly. What are the limits?
Which kind of leaves us with a final thought to chew on, maybe. Given where we've come from, these foundational ideas, what are the current limits?
Yeah, where does computation hit a wall right now?
And where might the next big breakthroughs actually happen? What could redefine automation as we understand it today?
Something to think about. Where does it go next?